In this video, I'd like to introduce a new topic. We are going to continue talking about motion and kinematics, but in a way that's a little bit different from what we have been talking about before. And I'd also like to talk about vector addition in a way that we have not done previously in this course. In the past in this course, we have talked about objects that are traveling at a constant velocity. So for equal periods of time, an object that is traveling at constant velocity will travel equal distances in whatever direction it is pointed. So the car in this slide here is shown at different times. It is moving equal amounts of distance in equal amounts of time. So v subscript 0 equals v subscript 1 equals v subscript 2 equals v subscript 3. We have also talked about objects with constant acceleration, which means constantly changing velocity. Each instantaneous v has a dv added to it. So v initial plus dv equals v1, and v1 plus dv equals v2. And as the instantaneous velocity increases, then the distance traveled in each time period increases. Let's take a look at that vector addition in a little bit more detail visually. I have a vector v initial, and I'm adding to it a dv. That delta v is added to v initial in such a way that the delta v vector starts at the end of the v initial vector. And then our v final is the result of v initial plus delta v. V final is drawn so that it starts where v initial started and ends where delta v ended. Recall this slide from early in the course. Velocity and delta v do not need to have the same direction, but delta v and acceleration must have the same direction because acceleration gets its direction component from the delta v vector, not from the velocity vector. Keep in mind also that the net force must be pointed in the same direction as the acceleration, and therefore is in the same direction as the dv. When the velocity and the delta v are in the exact opposite direction of one another, the object slows, meaning its velocity vector continually gets smaller due to the addition of dv to the instantaneous velocity. The way that works is the exact same method as we saw earlier. We have a v initial vector, we add a dv to it so that the delta v starts at the end of the v initial vector, and the v final vector is drawn so that it starts where the v initial started and v final ends where the delta v ended. Our new topic is the kinematics of an object that is moving at constant speed but is changing direction. Since the velocity vector includes the direction, if an object is traveling at constant speed but changing direction, then we know it is experiencing a dv, which means it is experiencing an acceleration. And by Newton's second law, the object is experiencing a non-zero net force. How that works specifically for constant speed in a circular path is what we're addressing now. Visually, this is the same process as before, but v initial plus dv, we don't want to get a v final that is a different size from v initial. So how are we supposed to do that? A useful thing to do would be to consider this in two dimensions so that v initial plus dv equals v final. And in this arrangement, it is possible that v initial and v final are equal in magnitude. As the time interval approaches 0 between v initial and v final, the delta v approaches a limit as well. And visually, v initial and dv still give a v final that starts where v initial starts and ends where delta v ends. If v initial equals the magnitude of v final, then the angle between v initial and delta v approaches 90 degrees. Thus, for an object traveling at constant speed, traveling in a circle, we know dv, a, and the net force are all perpendicular to the instantaneous velocity. This means that the acceleration of the object and the net force acting on the object at any given moment are both directed toward the center of the circular path that the object is taking. If dv is not perfectly perpendicular to the velocity vector, then that means some component of the dv vector is perpendicular to v initial, but some component is not going to be, meaning you have a dv perpendicular component that is causing the car to change direction, you also have a dv parallel that is in the same direction as v initial, meaning the car is speeding up and it is turning while it does so. It is also possible that you have a delta v that is causing the object to have a turn and a slowing down, depending on whether the parallel component of the dv is parallel in the same direction or anti-parallel to the v initial. Regardless, those are two scenarios where the object is not at a uniform speed, so they are things we might touch on, but the term uniform circular motion will be your first clue that the object is not speeding up or slowing down, it is just turning in a circle. So the net force and the dv and the acceleration vectors all point to the middle of the circle. That is to say, for circular motion, the magnitude of the initial velocity and the final velocity between any 2 points are equal. The velocity is always tangent to the circular path, and the acceleration of the object is radial, pointed into the center of the circle. We do have a few new terms I'd like to make sure that we touch on, sort of new terms. We're talking about kinematics and uniform circular motion and other related topics that will be coming up soon. These terms will be very important. So we want to make sure we're clear that capital T is talking about a measure of time, just like lowercase t was. However, we use capital T to denote that we are talking about a cyclic period, a repeated period of time. So the amount of time it takes an object that is traveling in a circle to complete one full circular path, we would refer to as the capital T, its period of motion. We also have this lowercase omega. Please do not get in the habit of calling it a W. I know it looks like one, but it is a lowercase omega. That is the angular frequency of the object, which is how many times it does a full cycle per second. The units for that are seconds to the -1 power, or sometimes referred to as hertz. I will also note that in the reference frame of the origin of the circle, the position of a particle that's moving in a circular motion in the x is cyclic and sinusoidal. That is, x as a function of t is sinusoidal. Also, y as a function of t is sinusoidal. That means that the location of the particle as it travels in circles can be represented as a function of time by this equation in the x and t simultaneously. Of course, this assumes a specific starting point, which is where exactly? When time is equal to 0, where is the object? I'll ask you about that in class and see if you can be clear about the answer to that based on this equation. Also, we can take the derivative of this equation to indicate that the velocity as a function of time for a particle traveling in a circle, its speed is constant, but its velocity is not. And the velocity as a function of time can be given by this equation right here, which is the derivative of the position as a function of time. And of course, the acceleration is then the second derivative of the position equation. So the acceleration as a function of time is given by this equation. So for an object moving in circular motion, its position as a function of time is not usually most convenient to describe in Cartesian coordinates, and would instead best be given as a r and a theta, where r is the radial distance and theta is equal to omega t, the angular frequency times the time elapsed. So this is our new topic, the kinematics of moving in circles, and we will use it to talk about the dynamics or forces of uniform circular motion, and then we will take this same information and move on to talking about energy and other topics. I do recommend you take a look at this slide, which is from the summary from OpenStax at the end of Chapter 4 section on circular motion, and of course I recommend that you take a look at the text, and I think a lot of this will, as with all of our other topics, will make more sense as we do some example problems. So we'll do that in class.